Last time we saw the analysis of a bipolar junction, and we said that the bipolar junction have to do the DC analysis that it's in the active mode, right? So that when it's in the active mode as an amplifier, when it works as an amplifier, that means you can amplify your input voltage to a higher output voltage or a lower depending on the output. Today we're going to focus on the AC analysis. And one thing you got to keep in mind, AC analysis, your transistor is going to follow the circling right now. This model that we're going to have to replace your circuit with this model. You can't just is and do AC analysis. This model right here is called hybrid pi model. Your lectures with your professor, you might see another model. And if you follow the T model, I just think you like, why would you do that? Hybrid pi is so much more simpler, and you can can actually get through it. So please don't use. And for AC analysis, before I get there, actually, this is the base of my transistor. So if you have a transistor, the base, this is the emitter, and this base right here is this section right here. And then the emitter is just the emitter itself. Terminal, and the collector is connected to this beta IB current dependent currents. So, so here you see that's IB, that's the base current. The IB is actually the current. This current dependent current source depends on the IB current that flows through the base. Also, one convention thing is when we're doing DC analysis, we tend to use capital letters, and when we're in AC analysis, we use small. So that's why we use IB like that. It's just to show professor or the person grading that you understand the distinction between and DC analysis. Okay, so what does AC analysis entail? I calculate the voltage AV. That's what the that's the output voltage over the input voltage. I'm gonna calculate the input resistance. That's gonna make sense. Second, overall voltage gain EV is V out big, and then the current gain is I output over output resistance. To achieve this, you need to disable all DC sources in your circuit. Why would you do that? Because we're working everything that's DC. Short circuit all capacitors, right? If you remember from circuit theory, the impedance of a capacitor, right? So it goes to infinity, something like this. Xc is equal to IF, something like that. So when this value is very high, right? One, that is zero. So your capacitor impedance it goes, so your capacitor becomes okay. And we want to replace the BJT by that we just saw here, the hybrid pi model. So without further ado, given this sort of situation, right? Okay, this circuit might look super big at first, but trust me, it's not that. This video, I am going to be writing everything. Okay. The first thing I want to do is identify the base emitter. Okay, and I want to disable my DC sources. What's going to happen is I'll place this circuit, and I'll disable all DC sources. This is VCC. It has to go to ground. This VCC has to go to ground. There we go. Those are the two DC sources in my circuit. Disable. Number two, I need to short circuit all capacitors. Short circuit. This capacitor. This capacitor. There we go. Now we can notice a couple things here. First thing we can notice is here, the here. This voltage is the same for both, and this voltage is the same for both. That means the resistors are parallel. Parallel with RB. Okay, that's one thing. Number two thing is here. This voltage is the same for these two. Both of them are connected to ground. So even though it is at first, so we're actually in parallel. So over here, I'll just RC parallel with. So that's the second thing I noticed. Third thing I noticed is that here, this resistor is connected to ground from one and is connected to ground on the other end. So that means this resistor is short. It doesn't even exist anymore. Not part of the circuit. Okay. So now cleaning things up, I can clean up the circuit a little bit. Our circuit becomes something like this. So we have our now I'm just gonna do the connections. So this base right here, and this is connected to this RB1 pair RB1 that's connected to it. And this a continue is connected to R sig and V sig. Ongoing sig V sig. There we go. And now if I look at my collector, this collector right here is connected to this resistor combination called RC parallel with RL. Just here L. And the voltage across RL is the same across. Why? Because they're in parallel. So this V out, it doesn't matter where I take it from. I take it from this here. It's the same thing because they're in parallel. Here, so I'll just take this RB and RB. Now, if I look at my RE, my emitter, this emitter is connected to this resistance, which is connected to ground. So we have E is connected to ground. There we go. All right, beautiful. So this is what our circuit looks like. So we've short circuited all capacitors. We've disabled all DC voltage sources. So now the only thing that's left to do from here is to replace a transistor with a small signal model and then actually find out what the gain is. Now that's going to involve a little bit of circuit theory and a little bit of algebra. So if you keep track of your variables, you're going to be able to achieve this. And one more thing you want to keep in mind is your voltage gain is going to be an expression, a mathematical expression composed of resistances, transistor elements. Your voltage gain should never depend on a current or a voltage in the circuit, otherwise it's wrong. You cannot have a voltage gain that's dependent on a current or a voltage gain is a constant value, all right? Factor by which your input voltage has increased or decreased or flipped over. So that's a constant, all right? It could be negative, it could be positive, but it's a constant. Okay? So now what it will do is we'll replace our transistor by a small signal model. And so to do this, I recommend drawing the small signal model first and then doing the necessary connections. So here I have my small signal model is basically the same thing here, and you're gonna have to memorize this, right? You're gonna have to memorize this. So I'll go back here. This is my base connected to R pi, and R pi and values like that. There are equations you can compute them. You will see those in further videos. This is V pi, and here I have my current dependent current source is beta I collector emitter. Now I'll just do the necessary connections. Here, my base is connected to this thing, right? So I have RB1 parallel with RB2, and that's connected to ground. And this is connected to R sig over here. R sig is connected to V sig. And mind you, V sig is a AC source, so that's why I didn't disable it yet. Emitter is connected to the emitter resistance. And the collector is connected to collector resistance. Now, there are multiple ways to find the gain of the circuit. I'm just going to show you a methodology that works for me, and if you follow it and practice with the same methodology, It's kind of a step-by-step process for you to be able to find your gain. Okay. So now if I go up a little bit, I will notice that in the circuit here, this is V sig, and then this is V input. So if I want to find V out over V in, it's this voltage that I need to consider. I need to find the ratio between this one and this one. So I can completely ignore this part temporarily because the only part of consideration of the circuit is this box right here, right? V out over V in. That's what I'm trying to find. So this is what I'll do. And one more thing, um, you might remember from the previous lecture, a value, a constant called beta, and that's a transistor, like it's associated with a transistor DC analysis. And there's something called there's resistor transfer rule, right? I'm just gonna write it right here. Transfer resistor rule. Transfer resistor. And the reason you want to do that is because usually when we work with amplifiers in the AC analysis, you want your emitter to be grounded. Why do we want your emitter to be grounded? It just facilitates the analysis and it's easier to find your equations. In this case right here, our emitter is not grounded. The emitter is connected to this resistor, right? We want it to be connected directly to ground. There's a way to make that happen. Resistor transfer rule tells you to bring a resistor from emitter to base. It must be multiplied by beta plus 1. So if I want to take this resistor from the emitter and I bring it to the base, I must multiply this resistor by beta plus 1. So then I can have my resistor right here, it would be Re beta plus 1, and then my emitter would be grounded. All right, if you that's the resistor transfer rule. You just trust, you have to trust and accept that the way this works, there is no proof, it's beyond the scope of this class, and just use it. Okay, it's going to make your life much easier. And like we said before, our Vn is right here, Vn, so we can ignore this part of the circuit temporarily, and we'll focus on this part of the circuit right now. Okay, so I'm just gonna copy this and then paste it right here. Here we go. So here you have your Vn minus plus Vn. Beautiful. Okay, and now I'm gonna take my emitter resistance and bring it to the base, so I'll multiply by beta plus 1. So what happens is my emitter is now grounded. Here I have a new resistance. I have a new resistance. Its value is Re times beta plus 1. Okay. And mind you that this V pi is only across R pi right here. Plus minus V pi. V pi is only across R pi. Okay. So now I want to find my voltage gain. So how would I do this? First, I know that this current right here is IB, and then I have another current called beta IB right here. So I already kind of see that I can write equations in terms of IB. And I know that this voltage right here, this is Vn. Okay, so IB, using Ohm's law, IB would just be Vn minus 0 over the sum of these resistances right here. Because this voltage, right, is the same. This voltage is between the base and the ground. And this is the base and this is the ground still. It's like these 2 points are connected. So this voltage right here is the same across the voltage of these two resistances. So IB would be Vn over R pi plus beta plus 1 times Re. So that's my first equation. This is my first equation. Okay? And the second equation I can see is, if you look over here, this is an open circuit. And we know that the current flowing through here is beta IB. So that means the current flowing through this resistor right here has to be beta IB. So again, I can apply Ohm's law. We have 0 minus V0 over RC parallel RL is equal to beta IB, because I know the current here is beta IB. So I have 0 minus V0 over RC parallel with RL, and that's equal to beta IB. Okay, so Now guess what? I have IB, I have IB in terms of Vn, and my goal is to find a ratio between the output and the input. So I can take this IB equation that I have right here and sub it in for the IB here. So that's what I'll do. I have minus VO over RC parallel with RL, and that's equal to beta times IB, which is this thing right here. Vn over R pi plus RE times beta plus 1. Okay, now I just need to find V out over Vn. And so AV, which is my voltage gain, is V out over Vn. Okay, so you have V out here, you have V in here, you do the necessary algebra, you will find that it's equal to minus beta RC parallel with RL, okay, divided by R pi plus RE times beta plus 1. So this is going to be your voltage gain expression. Now you might say the voltage gain expression is negative. What does that mean? It just means that so your input voltage, right? It's sinusoidal. It just means that there's a 180-degree phase shift. That's what that negative sign means. And this value right here is the amount by which your input amplitude has been either increased or decreased. Okay, so that's what this equation tells you. So this is how you find the voltage gain, AV. And now if you want to find the input resistance, how would we find the input resistance? So if you look at the circuit here, okay, this situation, first you have to notice that, where's my laser? Okay, there you go. First you have to notice that the V input is right here. So that means looking at the input resistance, it would be right where the input is, okay? So we're only considering this part of the circuit from the input terminals, right? The input terminals are right here, so only this part of the circuit will be considered. We can forget about this for the time being. So that's what we'll do, okay? So we have, our circuit is still the same thing as here. I can still copy paste this thing, copy, and then paste. Okay, so now I'm just gonna clean this thing up. RB1 parallel with RB2. So how do we find the input impedance or input resistance of the circuit? The input resistance is basically telling you replace, all right, you have these terminals right here. So you're here, you're trying to find Rn, a resistor value that can replace all of the circuit, right? This is Thevenin. We want to find a resistor value that can mimic all of the circuit, right? That's going to take the same voltage and the same current. That's our goal. Because if you're working in a lab, it's easier to talk about voltages and currents than a whole circuit itself. And the best way to do that is talking about a resistor value. All right, what's the input impedance on the circuit? Instead of talking about, oh my God, this circuit has yeah resistors, or this many transistors, or anything like that. It's much easier to numb it down to one thing and then talk about it. So what I'll do is, where if you look at the circuit, we're talking about the base. That's where we're trying to replace this circuit. So if you look at my AC situation here, this is the base. So that means here I need to connect a VT voltage, and I need to give 1 ampere into the circuit, 1 ampere, to be able to find the value of VT. And once I find the value of VT, that's going to spit out the value of Rn, because that's the way Thevenin works. So by the way, remember the emitter was grounded. Why? Because of the resistor transfer rule. So this is grounded. That's it. And then here we have Re times beta plus 1. Okay, now I can notice one thing right away, right off the get-go here. I can notice that these two resistors are in series, and that these voltages are the same here for these two resistors, and both of these resistors are connected to ground. So what does that mean? That means that these two are connected in series, which make up one resistor, which is in parallel with this one. So I'll just clean things up here. So we have our plus minus VT, 1 ampere into the circuit, and then we have one resistor only, and that resistor would be R pi plus Re times beta plus 1. Okay, that's the series combination. And this is in parallel with RB1 parallel with RB2. And then this is connected to ground. Okay, and then the rest of the circuit is involved where we have a current dependent current source, beta IB, and then this is connected to RC parallel with RL. Okay, and this 1 ampere is going into the circuit, by the way, Thevenin convention. So I'm just going to double check in my notes real quick if I have everything right so far. Check the gain expression here, minus B. Yes, gain expression is perfect. And then resistor combination here. Okay, there we go. So now if you see this kind of situation here, you will find that this current is going in this circuit right here. You know the current going through this resistor is 1 ampere, and you know the voltage across the VT. So VT is equal to, well, 1 times the resistance. And what is the resistance? It's this thing. So I'm just going to copy paste this thing. Copy, paste. So VT is 1 times this thing. And we said that if we find VT, we find Rn. So that means that Rn is equal to whatever we pasted, paste. So this is the resistor. This is the input resistance, all right, of this circuit. The input resistance of this circuit is denoted by this expression. There we go. And the reason it's helpful for you to learn to use variables instead of actual numerical values of your resistors in your circuits. And why do I say that? Because a lot of electronics is just variables, and then you plug in the values at the very end. And sometimes you might not be even given values, right? You just do everything in variable form. So here, if I double check my resistor gain, the input resistance expression, it is correct. So we found we found this. This has been done, and this has been done, and now we want to find the overall voltage gain. And usually, the moment you find this thing, the rest follows from this, right? You will see in a minute why I say that the voltage gain here, the overall voltage gain, is going to depend on this. So now let me show you here. If we want to find the overall voltage gain, GV is equal to V out over V sig. Okay. Now I can kind of break down this. There's a minor trick to do this. It's V out over V sig, right? With this one we're trying to find V out over V sig. So we want to have V out over V in times V in over V sig, right? That's kind of the trick. We take V out over V in times V in over V sig. And why do I do this is because here the V input cancel out and we're back to V out over V sig. So when you're given, you want to find the overall voltage gain, V out over V sig, just write it as V out over V in times V in over V sig, right? Because it ends up being the same thing. So I'm just going to remove this right now, and I won't do the cancellation. So we have VI, oops, we have VI here, and we have VI here. Now, if you're smart and you kind of notice something, this is my voltage gain that I found earlier. So I have my voltage gain times VI over V sig. The only thing I need to find is VI over V sig. So if I look at my circuit before I remove this, so if I look at this circuit right now here, when V sig was still involved, okay? Now remember that this V input right here, I'm just going to do it in orange, this V input, we kind of had our input resistance there, right? We found the corresponding input resistance of this circuit. We know that we can replace all of this by the Rin value that we found, okay? So our circuit, essentially, everything here that I'm boxing is a resistor. We can replace it by a resistor. So this R sig is going to be connected to some resistor value and connected to ground, right? All of this can go, and I have only this thing remaining on my circuit, right? I'm replacing all of this with my input impedance, and it's going to be right here. So all this goes away. Why? Because I replaced it by the input impedance that I computed. So my circuit becomes like this. Here I have plus minus V sig. I have R sig, and here I have R input, right? Everything in that circuit, including the small signal model, can be replaced by R input. Now, the voltage across R input, as I said earlier, is V input minus plus V input. Now, I want to find a ratio between V in and V sig. So if you look at this circuit, these two resistances are in series, so I can use voltage dividers. So V in would be equal to R in over R sig plus R in times V sig. That's the voltage divider expression. So if I divide both sides by V sig, I find V in over V sig, which is R in over R sig plus R in. There we go. I found it. So this is the value of V in over V sig. So that means I can take the value that I found here, and then I can take this expression and plug it in here. Okay. So that means GV. Oops, why is it in red? So that means GV, which is my overall voltage gain, is going to be AV times Rn over R sig plus Rn. Now, what are the values of AV and Rn? If I look up, okay, if I look up here, this is AV. So I replace AV by its value here, AV times the value of Rn is right here. This is what we computed before. So this is Rn over R sig plus Rn. So the thing that I have in the numerator already. And this is going to be my overall voltage gain. Now, this expression is big and scary, but the process to find them was very simple, right? It was pretty quick. Everything that we required was already given to us. We just had to put it all together by doing circuit analysis. So this is my overall voltage gain. So now we can say that this has been found as well. And the next thing we want to find is the current gain, AI, which is I output over I input, okay? We want to find the I output over I input. So now, if you look at this sort of situation here in the circuit again, now if you say that this is the input voltage, boom, boom, all right, minus, this minus plus, and this is the input, this is the ground, okay, and this is R input, it's logical to say that the current flowing through the R in would be the I in, all right? You have input impedance, or I should rather say you have input resistance. The voltage across the input resistance is a V input. It's an input voltage. So the current flowing through the resistance has to be the input current, right? So here I have I input here, I input. So here I can just use Ohm's law, right? I input would be V input over R input. So that's what I'll do. I input is equal to V input over R input. Okay, that's my first expression. I input is equal to V input over R input. Okay, so that's my first expression here. And now I want to find the current gain. But if you think about it, oh, my leg's cramping up. What the hell? Oh my god. Oh my god. If you're watching this, oh my leg. Whew, had a martial arts training this morning, so my whole body's shaking up. My whole body's shaking up right now. One sec, give me a sec, give me a sec, bro. That's the thing about making these videos is that I'm usually so busy at work usually, and then on the weekends I train, on the weekdays I train, so I just finding time to make these videos, and now you're gonna watch me cramp up in the video. Whew. Okay, I think it's getting better now. Okay, can keep can keep on going here. Let's get back on topic. Okay, so the current gain AI is going to be the I output over I input. Okay, so I have I input in terms of V in and Rn. Now I need to find the I output. So if I look over here, well, there I find that the voltage, output voltage is right here. So it's logical that the output voltage would be flowing. Let me look at the original circuit. What's the original circuit? There we go. The output voltage is taken across RL, right? So it makes sense that the output current will be taken across RL, right? Make sure, because this is a physical circuit, right? When you're measuring the voltage of this circuit, you're measuring it across resistor RL only. Yes, you can measure it across RC and it would be the same. However, the current flowing here and the current flowing here is not I out, right? Because the voltage has been taken across RL, what that entails is that the current flowing through RL has to be I out, right? Because you're choosing to measure it from RL, and that's given by the circuit. So that means, it means one thing only. It means that this is I out, and I out would be V out over RL. So this is my next expression. I'm going to write it down here. So I out is V out over RL. And this is my second expression. Now um, I have my output returns in terms of V output and input in terms of V input. So I'll just replace them. So I output would be V out over RL divided by I input. But I input, I'm doing divided, so I'm just going to multiply by the reciprocal of this thing that I have here. So it becomes R in over V in. So neat. Now I can see something going on here. This is V out and this is V in. V out over V in is just AV, which is my voltage gain, times R in over RL. So now, if I remember correctly, my voltage gain expression, so everything ties back to the voltage gain. If you find the voltage gain correctly, it's a freebie question and it's worth a lot of marks on the final exam. So you do that correctly, you're basically going to pass the course, I'm telling you right now. So this is AV, and then Rn is this value here. Times Rn divided by RL. And this is our expression for the current gain. Okay, so this is the expression for current gain, and if I double check the expression, we got it correctly again. It's not that hard to obtain these expressions. They look big and scary, but they're not that bad. So we found the current gain. The only thing that's left for us to do is to find the output resistance, okay? So we're gonna find the output resistance here. So let's go back to this main circuit that we had going on here in red. So this is what we got going on. I'm just gonna copy paste this thing. If you have an iPad, copy pasting your circuit saves you so much time, because imagine having to draw that over and over again. I'm just so glad I have one. There we go. So I'm just gonna erase this Rn for a minute. Okay. And now what that means is I'm not trying to find the output resistance. So that means I need to go to the output, which in this case is right here, and I need to connect a V here, V and given one input, 1 ampere current. So that's what I'll do. So boom, at the output here, V oh, an ugly circle, V plus minus, and this is 1 ampere current flowing into the circuit. And then here, now remember, when you're doing Thevenin, you disable all of the independent sources. So this one, even though it's AC, it's still independent source, so you're going to disable it. So it's going to be connected straight to ground. There we go. Okay, so we have this sort of situation going on here. And remember, because I copy pasted the circuit, this emitter is still connected to the resistance, but remember that we did the switch to resistor transfer rule. So this is beta plus 1 right here. Okay, and then this is connected to ground. By the way, this can get pretty overwhelming. We're getting through a lot of information right here. Finding gain expressions for amplifiers is something, it's a skill, right? It's a skill that you have to build up. So I would suggest after you watch this, try to find everything by yourself. Make sure you get them right. If you don't get them right, go to the video and watch it again to try to see where you kind of did not understand the stuff. And then you can watch the video and try it again until you get it, right? It's a very important skill. And to build up that skill, the best way to build it up is to practice. Okay? So we have this sort of situation going on here. So now, let me erase this highlighted here. We have our sig, which is connected to ground. Now, piece by piece, I'm going to work piece by piece. I'm going to clean this up. I'm seeing a lot of resistances here. That means there are room for some combinations here. So this R sig and this terminal here is the same. So RB1 parallel with RB2 and R sig here, they have a shared terminal. And if you look at the other terminal here for R sig is connected to ground, and this one is connected to ground, so they're sharing this one. So these two are in parallel. We have R sig parallel with RB1, parallel with RB2. Okay, and now if you look over here, I'm just gonna do yellow. These two resistances, these two are in series. So here we got R pi plus RE times beta plus 1. Okay, now all this is one resistor. So if you look at this thing right now, if I clean things up, we have something like this. We have ground connected to R sig parallel with RB1, parallel with RB2. Okay, so that's what I have so far. What I did here, I just replaced all of this by that, and then it's connected to the base. So here I have my base, and then this base is connected to the series combination. This base is connected to the series combinations, R pi plus RE times beta plus 1, which is connected to ground, okay? Or I should draw it this way so it's a little bit more obvious. It's just connected to ground, and this is beta IB, and then here we have RC parallel with RL, and then this is connected to VT. By the way, one thing you gotta keep in mind again, because I'm copy pasting and I know my circuit, my electronics pretty well, is you have to make sure, because here we did a combination, so you have to account for that, right? When I chose this circuit as my reference, this combination was already made. But if you look at the initial circuit, this combination was not made. So if you look over here, V out is only across RL, right? It's only across RL. So when you're doing Thevenin, um it's the RC is not, it's not parallel with RC, so you have to only have RL there, okay? So RL is not even here. It's only RC that's considered. Because if you look over here, I kind of missaid that earlier because the voltage here is V out, right? So I can ignore this and look at the circuit right here because the voltage here and the voltage here is the same anyways. So the only thing that's left is the RC. They're not in parallel here because this point, all this is the same voltage, right? All this is the same voltage, right? And also, when you're doing output resistance is going to be pointing to the output voltage right here, which is not considered RL, right? It considers RC because we haven't done the combination in the initial circuit. That's how it was given to us. It was just told that the output is taken at RL. That's it was given to us. We have no choice over that. So we have to make sure here that when we're copy pasting our circuits, we're being very careful that we're not considering the RL as well. Okay, so now that I have this, I can realize that these two resistors are in series. So I just remove one of them, and I'll just write here plus R pi plus RE times beta plus 1, and then here I can do the connection. So now I notice that this resistor is connected to ground on this side, and it's connected to ground on this side. What does that mean? The resistor is short-circuited, so this resistor does not take part in that circuit. So your entire circuit, basically, it when a resistor is short-circuited, it just means there's no current flowing through it also, by the way. That's another thing. So this current right here, IB, is equal to 0 because the resistor is short-circuited, okay? So now, if IB is equal to 0, that means this is equal to 0 because it depends on IB. So even this is removed from the circuit, and your entire circuit simplifies down to this. And since you're giving 1 ampere current into the circuit, it just means that VT is equal to RC. And if you find VT, you find your output impedance. That means that R out is equal to RC. And that's my output impedance or output resistance. So this is the step-by-step process to do AC analysis, and I understand that it can get kind of overwhelming, especially most professors these days. I don't understand why they skip on so much things when you're doing AC analysis. It's very important. It carries on to electronics too, and you know anything that has to do with voltage gain and stuff like that. So watch the video over and over if you need to. Watch the full length, try it by yourself, and if you don't understand, go back to the video and try to understand it again. So everything that I presented here is a step-by-step process that can help you find those voltage gain, overall voltage gain, input output impedance, and the current gain. With that being said, I think this is the end of the video. We're going to do more examples like that in the future, in future videos. And if you want to see more content from an unconventional small YouTuber, just click on that subscribe button, and don't forget to put in comments and like if you want to. And I think that's all I got for you today. Where is it? Stop recording. Where is it? There we go.